Hello everyone, welcome back to Turning Turing. Today we're tackling merge sort, a powerful sorting algorithm based on divide and conquer strategy. In this video, I'll try to explain the concept, try run an example, write C++ code, and discuss its efficiency. So let's get started. Merge sort is actually like solving a puzzle by breaking into smaller and manageable pieces. So I'll try to explain merge sort using an example. Let's say we've been given an unsorted array 8, 3, 6, 2. So the first step of merge sort is keep on dividing the array into two equal halves till you are left with arrays of just size 1. So we'll divide it into two equal halves. We'll have 8, 3, 6, 2. We'll further divide these arrays into halves. We'll be left with 8, 3, 6, 2. Now the first step of the algorithm is over, where we divide the array till we're left with arrays of size 1. And as you can see, the last level of this tree has all the arrays of size 1. And an array of size 1 or an array which only has one element is always sorted by default. So what we do is that we keep on sorting the halves as we move above in the tree, and we keep on combining these sorted halves to give us a bigger sorted array. So the next step of the algorithm is sorting the halves and combining them to give a bigger array. So that's why it's divide and conquer. First we divide it into smaller parts, then we conquer these halves, and then we combine it to solve the bigger problem. So 8, 3 are already sorted by default because arrays of size 1 are sorted. We move up. Now we combine these sorted halves to give a bigger sorted array. So when we combine these, we'll get 3, 8. Similarly, when we move up, we'll combine these two to get a bigger sorted array. So this will be a sorted array. Now we have two sorted halves. We'll again move up in our tree and we'll combine these sorted halves. When we combine these sorted halves, the final array will look something like this. And at the end, we'll have a bigger sorted array. Or at the end, our complete array will be sorted. So this is how merge sort works. And we can do this divide and conquer recursively. Let's try it out on another example, on a bigger example. Let's take 3, 10, 1, 7, 4, 8. So divided into two halves, 3, 10, 1, 7, 4, 8. Again 3, 10 and 1. This will be further divided into 3 and 10, 7, 4 and 8, 7 and 4. Now all our leaf nodes are arrays of size 1. So we start moving up in the tree and combining the sorted halves. So 3 and 10 arrays of size 1 are sorted by default. We combine them to give us a sorted array, and the sorted array will be 3, 10. Now array of size 1 is sorted by default. So we'll combine the two sorted halves to give us a bigger sorted array, and the sorted array would look something like this. Similarly, 7 and 4 will be combined to give 4, 7, and these two halves will be combined to give 4, 7, 8. Now we have two sorted halves. We'll again combine these two sorted halves to give the final sorted array, and the final sorted array would look something like this. Now I hope that you've understood how merge sort works. So let's look at the implementation of merge sort. So first we've defined merge sort method. Merge sort method is the main method that will be used for sorting. Input is a vector that needs to be sorted, and we have the left and right bounds of the array. So initially these will be passed as 0 and n minus 1, the start and the end of the array. So our first step is to find the mid of this current array, because our first part of the algorithm is to keep dividing it into halves till we are left with arrays of just size 1. So we find the mid and we divide it into two halves. The first half is actually going to be array from left till mid, and the second half is going to be from mid plus 1 to right. So these are the two halves, and we have delegated our task to sort these halves to the method merge sort. So in recursion, we always assume that we'll do our duty of the current step, and for the smaller problem, we'll just delegate it to the recursive function. So we assume that recursive function will work and it'll perform its duty for the smaller problem. Now using the answer for the smaller problem, we just need to compute the answer at the current step. So we've delegated the task to sort these smaller halves to the same recursive function. And once the recursive function has sorted these smaller halves, our step is to combine these smaller halves into a bigger sorted array. So both these smaller halves will be sorted when returned from the recursive function. And we have passed it to a helper function merge, which is essentially combining these two sorted arrays into a bigger sorted array. So as we discussed that we are going to break our array into halves only till the point we are left with arrays of size 1, because when we are left with arrays of size 1 they are sorted by default. So we've put this condition to check that, because when left is less than right, that implies that there are at least two elements in the array. When left becomes equal to right, we'll be only left with one element in the array. So till the time left is less than right, we are dividing the array, but as soon as left becomes equal to right, we do not need to divide it further. Now this is our helper method merge, which is used to combine two sorted arrays to give a bigger sorted array. Now this we have already covered as part of our array series, and this merge function is pretty trivial and simple. So I'm not discussing this merge function in detail, but this is essentially going to combine the two sorted halves into a sorted array, into a single sorted array. And as a good exercise, I would want you to implement the merge function on your own. I will add this code in the description as well, and you can pause the video to see the code here as well. But I would prefer that you do not look at the solution and you try to implement it on your own. So merge sort is pretty simple. There are only two steps: divide the array recursively and combine the two sorted halves into one. So the next part to discuss is the time complexity and space complexity for merge sort. So let's try to compute the time complexity for merge sort. Let's assume that the array was x comma y comma z comma a. We'll have x comma y z comma e, and then we'll have x y z and e. So whenever we try to break down our arrays into half, how many levels do we have in our tree? So at each step, our array size is decreasing by 2, and we do it till the time we are left with arrays of size 1. So if you have an array of size n and you need to reach to array of size 1, and at every step you divide it by 2, so how many times do you need to divide it to reach from n to 1? So as you would know from simple geometric progression that there will be log n steps, or you would have to divide it log n times to reach 1. So the total height of the tree is going to be log n. And as you can see that at every step merge is going to take big O of n time. So there are two operations here, two operations of merge here. At this step you have four operations of merge. So in total at every level or at every step in the tree there will be n operations in merge, so that will be big O of n. So there are total log n steps, and at each step merge is going to take n. So the total time complexity for merge sort is big O of n into log n, and this is going to be the time complexity for merge sort in best case, average case, and worst case. Now coming to the space complexity. So for our helper merge function, we are using an additional array of size n. So the space complexity turns out to be big O of n. So merge sort is significantly faster than insertion sort for large data sets due to its n log n efficiency, but it uses extra memory unlike in-place algorithms. So some pros are that it's fast, and regardless of the size of the input, the time complexity is n log n, is therefore it's excellent for large data sets. And it's a stable algorithm. It retains the order of equal elements. Uh, some cons of merge sort are it uses extra space, so for large data sets there will be a additional memory overhead, and it's slower than other algorithms like quicksort for smaller data sets. So that's merge sort for you, an efficient and reliable sorting algorithm. I hope you found this helpful. In case if you have any questions, do drop them in the comment section below, and I'll see you in the next video. Till then, take care and keep learning.